Thank you very much for your kind introduction. First of all, I'd like to thank the organizing committee for giving me this nice opportunity to talk about research in the oral presentation session of this conference. Here is a fluorescent dipyrrin-typical-element complex responding to external stimuli. This study can be applied for the fluorescent sensing for a gas molecule or gas ion. Okay. I have already introduced a concept to my research briefly in my keynote lecture this morning, but I want to emphasize that our study on the cooperative and synergistic molecular systems for functional modulation is expected to contribute to future green chemistry. So here I want to talk about the novel fluorophores responding to external stimuli. If the fluorophores have near infrared emission, such kind of fluorophores should be very important and useful for bioimaging. Okay. So among the famous 12 principles of green chemistry, our research on the gas sensing by using fluorophores responding to external stimuli is closely related to analytical methodologies need to be further developed to allow for real-time in process monitoring. So, okay, so the dipyrrin is known to be a partial structure of the porphyrins. This molecule can be converted to the corresponding boron complexes, so BODIPY, very easily just by a reaction with the dipyrrin with the BF3 etherate. And BODIPY and its derivatives have often been used as a fluorophore for sensors, bioimaging, and OLED, and the solar cells, laser diode, and so on. Because the BODIPY and its derivatives have excellent photophysical properties, strong and sharp absorption and fluorescence, and high photostability. And the photophysical properties of the BODIPY can be easily tuned by introducing the suitable substituent into the framework of the BODIPY. So in particular, many examples of ion sensors based on BODIPY were reported. I show you some of them here, but all the examples, the BODIPY part were used as the fluorophore, not the binding site to gas molecule ions. Because, however, we expected that this BFT unit can work as a binding site because judging from the large difference in electronegativity between the boron and the fluorine, these fluorine atoms should have a sufficient negative charge on it. Which is suitable for the cation recognition. The electrostatic potential surface map obtained from the DFT calculations also support the enhancement of the BFT, the negative charge on the BFT, BF2 parts. So we designed and synthesized the macrocyclic and the linear oligo-BODIPY host for fluorescence molecular systems responding to external stimuli. So this is a molecule, macrocyclic molecule we first designed and synthesized. And we expected this molecule should provide a nice binding site for for example, alkyl metal ions, because the 6 fluorine atoms are arranged in the helical fashion. To cause a macrocyclic effect. This should be very important for the binding to cationic gas through BF metal interactions. This is noble interaction, but anyway, we expected this kind of interaction, which should be very useful to recognize cationic guest here. And this is a synthetic way to prepare the target molecule macrocyclic compound and also precursor of the macrocyclic ligand. So you can see we can get this molecule in reasonable yield, and also the conversion from this macrocyclic ligand to the desired tris BODIPY derivatives. The reaction yield is so high, almost quantitatively. And this is the X-ray structure of the macrocyclic tris dipyrrin BF2 complex. As we expected, this compound has a nice cavity and 6 fluorine atoms arranged in a so macrocyclic fashion. And the important thing is the size of the cavity. The diameter is about 4 angstrom. That is suitable for the cesium ion binding. So as you know, the detection of the cesium ion is very important in Japan. So you know, the radioactive cesium ion pollution is really a problem in Japan now. So many people want to prepare the highly cesium selective binders, detectors. And we examine the cesium ion binding by using the macrocyclic compound 1. This is the UV visible spectral titration experiment. So you can see the significant spectral change upon the addition of the cesium ion. Blue shift was observed. And using this chemical spectral change, we can get the binding constant. The log Ka is about 5.5 for the 1-to-1 complexation. So this means we achieve the reasonably very high cesium ion binding. Okay. I just summarize the results of the binding constant toward the alkyl metal ions compared to the sodium, potassium. The binding constant toward the cesium ion is much so large, so much higher than the toward the sodium and potassium. So we can achieve the cesium ion selectivity by using this macrocyclic system due to the macrocyclic effect, probably macrocyclic effect, and also the BF cation interaction. In order to clarify the macrocyclic effect, we examine the binding constant of monomer to the cesium ion. So as you expected, the monomer shows a very weak interaction. Log Ka is only 2.6. So compared to the macrocyclic compound, so this compound, the monomer shows a very low binding constant. The enhancement is about 750-fold. This should be caused by the macrocyclic effect. One more very interesting binding feature of the this macrocyclic compound is complexation with the secondary ammonium ions. We expected formation of the pseudo-rotaxan type complex. Then when we add the alkyl ammonium, this host, to the solution of the compound 1, we observe the spectral change. Then using this change, we can get the binding constant. The log Ka is 4.1. In contrast, in the case of dibenzyl ammonium, so no binding was observed. No spectral change took place. This means this result so strongly suggests the macrocyclic compound complex where this dialkyl ammonium guest with the pseudo-rotaxan structure, 1-to-1 complex. And we can see the significant fluorescence change upon the addition of the guest. So in the absence of guessed, the intensity of the fluorescence of this compound is very low. But when we add the secondary ammonium gas, the intensity increased dramatically. So we can see the change of the fluorescence with our naked eyes, as shown here. And proton NMR spectroscopy clearly indicates the formation of pseudo rhodexane structures shown here. So we can observe the NOE effect, nuclear overhauser effect between the protons between the host and the guest, as shown here. And finally, we got the X-ray structure of the complex. So the macrocyclic compound captured the ammonium gas inside the cavity to make a pseudo-rhodexane structure. And you can see the very interesting BF and proton non-classical hydrogen bonding here to stabilize the rhodexane structure. So this is a really fast example of novel BFH interaction, non-classical interactions. So as far as I know, we know that this is the first example of the formation of pseudo-rhodexane utilizing this type of the non-classical hydrogen bonding. And I just summarize the first topic. Macrocyclic twist dipyrrin BF2 complex shows a nice affinity, a selective affinity toward the cesium ion. And also this compound reacts with the dialkyl ammonium compound to give the corresponding pseudo-rhodexane through the non-classical hydrogen bond. Okay. And next topic is a linear dipyrin and a BODIPY oligomers bearing conjugatable spacer. We selected the phenol ring as a spacer to extend the pi conjugated system to achieve a redshift of absorption and fluorescence. So the near-infrared absorption and fluorescence is very important for bioimaging. There is a transparent window for the bioimaging at that region. Anyway, so here's the synthetic way to the target molecule shown here. You can see we can get the linear compound and also the target BF2 oligomers in reasonable yields. Right. The X-ray structure, I only show you the X-ray structure of ligand 2 dimer. So obviously, apparently this compound has a linear structure. And so this slide shows the absorption and the fluorescence spectra of a linear ligand L1 and from L1 to 5 in chloroform. So as we expected, the spectra, absorption spectra and the fluorescence spectra are shifted to longer wavelengths when the length of the molecule increased. Of course, the fluorescence efficiency is very low in the case of the ligand. But on the other hand, the fluorescence of the BODIPY derivatives is much higher than the corresponding linear ligand. But the very important point here is even dimer, B2, it's a dimer, the fluorescence reaches to the near-infrared region, 715 nanometers. Lambda max is 715 nanometers, with really high quantum yield, 65%. So this is really high compared to other fluorophores. Okay, compared to other fluorophores, so which emits near IR light. So it's almost, I think, the champion data of the efficiency of the fluorescence in this region. Okay, so next I examine the cesium ion binding using the trimer. I only show you the result of the trimer, but you can see this considerable change by the addition of cesium ion. We can observe, we can determine the binding constant, and I just summarize the results. As you can see, the trimer shows a nice cesium ion's selectivity compared to sodium and potassium. So, and the proton NMR spectroscopy indicates the interesting conformational change from linear to this compound B3 to complex. So I mean helical so structure is formed. So judging from the upfield shifts and ROE between the terminal protons of this ligand. Okay, and cesium ion recognition is detected by our own naked eyes. So in the presence of cesium, we can see the color change from blue to pink or violet. And we can see the emission of fluorescence and in the presence of cesium. So we hope this type of the linear complex can be used for the practical application, I mean detection of the cesium ion in the natural sources in future. Okay, so this is the last topic of my talk today, and other luminescence dipyrrin complexes. And dipyrrin can react with many kinds of metal ions to give the corresponding metal complexes, but highly emissive dipyrrin complexes are rare, except BODIPY and aluminum complex, which we have prepared recently, shown here. The quantum yield is about 72%. But more recently, we prepared a more interesting compound, highly emissive hypercoordinate dipyrrin silicon complexes. So usually silicon atom is a tetracoordinate, but this compound is a pentacoordinate, very stable when we use this ligand. And we treated with 1A with the tetrachlorosilane in the presence of int. After a treatment of wet methanol, we got silanol for in 41% yield. No siloxane was obtained under these conditions. But very interestingly, so when after removal of water, so I mean the silanol was dissolved in the hexane and the reflux for several hours, we can get the siloxane in more than 90% use. So removal water convert this compound to the siloxane. The X-ray structure of 5A clearly indicates the dimeric structure of this molecule. The two moiety was connected by mu-oxo linkage. And optical properties of these compounds are quite different. You can see the difference in absorption spectra and also fluorescence spectra. And the quantum yield of the silanol 4A is about twice as large as that of the siloxane 5A. So you can see the color change and the luminescence change with our naked eyes associated with the structural interconversion between 4A and 5A. So I don't have enough time to talk about the other typical element compounds, but last year we prepared the germanium analogs, and also this year we reported the tin analogs. They are also highly emissive. So we hope that this new type of dipyrrin complexes can be applied to new fluorescence materials responding to external stimuli in future. Finally, I acknowledge the co-workers, Dr. Yamamura and Ikeda, for their significant contribution to this work, and the former students Sakamoto and Takizawa for their hard work. Thank you for your kind attention.
Okay, we can take one question. Anybody have a question? Well, it was between you two here. Who's got? Okay.
I was just wondering, is there any possibility to introduce silanes, like instead of silanols, having silicon OH, can we put silicon hydrogen?
Silicon?
Yeah, introduction of silanes, not this silanols.
Yeah, pentacoordinate compound. In the case of pentacoordinate compound, silicon, silanol is more stable than the siloxane. So there are many examples about that.
I'm looking from different perspective. If you try to use triethylsilane or kind of hydrogen source, hydride source.
Hydrogen source.
Yeah. If you put
I see.
silanes, that might be quite stable reducing agent. However, it is not going to be green, provided you should be able to recycle it.
All right.
Yeah, here.
Yeah, the hydroxyl, this
Yeah,
source.
yes.
Yeah. So I use wet methanol. This methanol contains water.
Yeah, but still you should be able to do this by using some sort of non-protic solvents.
Yeah, so to remove this OH, so just mixing in the...
Put hydrogen there, hydride rather. That can be used as is quite a stable reducing agent.
Yeah, probably the intermediate is so SiClCl, and then this compound react with the OH and OH, and then the water attack this silicon to give this complex.
I'm just wondering, is there any possibility to synthesize silanes?
And in the case of the so use so this type of the 1, 2, 3, 4, 5 membered chelate, we can get this stable silanol.
Okay.
Okay.
Thank